Okay, now we are long time waiting and you might wonder what you don't know what you are doing here. But Hammermill, the company, produced paper for the laser printer. So standard paper width is a 216 millimeter or 8.5 inches. Suppose that the actual width is random variable. It's normally distributed with a target average of 216 millimeter, and a known standard deviation is 0.023 millimeters based on the manufacturing technology. Variation arises during the manufacturing because of slight difference in the paper stock, vibration in the roller. There's a lot of the reasons, so you can have a slightly different number. Now, cutter can be adjusted if the paper width drift from the target mean. Suppose that the quality control inspector choose a 50 sheet at random. So this is the sample, right? You choose a 50 sample and then measure, and then we find the sample mean is this one. So this is a slightly, so x bar is 216.0070. So n is 50. We know the sigma. Using 5% level of significance, does this sample shows a paper average width is greater than the target? So now this is just greater than the target. So null hypothesis will be, is it greater? So we got a slightly 216.00. Was it 7? Yeah, 007. Now this is greater than 216, but is it significant? So we are trying to do, if still the real mean is 216, what is the chance to get 216.007? If this is a rare, then we reject I0, because this is not, it cannot happen by chance, because the chance to get this number is pretty small. Rare means it's a small chance. Then maybe because our mu is greater than 216, that's why this happened, we reject. Or this is not rare and we fail to reject. Okay, from the null hypothesis is the mu 0 is a 216, so I want to know, is it greater or not? So alternative hypothesis is this one, and then we can find out the level of significance. So that's why it's greater or not, so that's why it's greater. So this is the right hand side, right tail test, and then 5%, so we have to find out the z value that created this is 5%. So simply you can look up to the z value. So we are looking for the cases, this is 5%, which means this is 95%. So you have to look up the 95%. Again, the 95% happening here in the middle, so it's a 1.6 and 45. So our z value will be 1.645. So that's why the z value with 5% is here. Right? So now we have to find out our z value. So our z value will be calculated in this way, because our x bar is this one minus the mean. So as I told you, we assume if null hypothesis is true. This is what our assumption. If the null hypothesis is true, what is the z value for the getting 216.007? And then since this is the x bar, so we have to use x bar's standard deviation. And then you calculate it here, and we find out z is a 2.152, which is greater than 1.645, which means since our case is here 1.645, what is the chance I will get the z which is greater than 1.645 is 5%. But I got a 2.15, which means it can happen way smaller than 5%. So still this is possible to happen even if the null hypothesis is true, but getting 216.007, assuming this is true, getting this one is rarer than the 5%. So which means probably this is not happening by chance. Probably because our mu is greater than 2.16, that's why this is happening. So we can reject H0, which means we conclude our mean is greater than 216, so which means we have to adjust the machine. Right? So our test statistics is 2.15, which is greater than 1.645, which means this is the really rare case. If we assume null hypothesis is true, getting x bar 216.007 is this is rare enough. To reject null hypothesis. So we can reject the null hypothesis. So difference is really small, but still this is a statistically significant to reject the null hypothesis. So now we take an action here. The action means we have to adjust the machine or whatever. So since we reject the null hypothesis, which means we have a strong enough evidence that the average width is changed, is greater than 216. So like readjust the machine setting or whatever, the resharpening the cutting tool, you have to do something to make your real mean go back to the 216. P-value method is it's not actually different method. We just trying to calculate the p-value instead of the comparing the z. So previously what we did is we find out we already choose the 5% confidence level. So we find out 5% here, and then we calculate the z, and then we compare the z. Our z is greater than this one, so we reject. So instead of do this, we simply calculate the probability of our z. Okay, and we calculated the probability. And then if this probability is smaller than 5%, then this is again the rare case, so we reject. So if you're gonna reject using the test statistics, then you're gonna reject the p-value method. So you cannot have a different result. either you use a test statistics method or p-value method, the conclusion should be always the same. However, are you gonna compare in the z-value, or are you gonna compare the probability? So the only difference is that the p-value is sometimes give a more intuitive result, because you can tell. So I wanna when you compare the z-value, actually z-value doesn't tell you exact what it means, but the p-value means what is the probability I can get a x bar that is greater or smaller, because when this is the left tail, then probability will be the smaller than. So that's why I'm just keep using the rare rather than smaller or bigger. So probability of getting those x bar is a smaller case, the rare case, then we're gonna reject. Again, how can we tell the p-value? Is what is the chance I can get a x bar that's smaller than this? What is the probability? If the probability is smaller than my criteria confidence level, then we're gonna reject. Right? So whether we use a critical value approach or a p-value approach, decision will be the same. So only which number we're gonna use because our z-value is tied to the probability. Remember, the z-value is tied to the probability. So are you gonna compare in the z-value level, or are you gonna compare it in the probability level? That's the only difference. But some people prefer the p-value because p-value is more easy to interpret. Then you can tell how strong your evidence is. But z-value, if you use the z-value, then sometimes you cannot tell how strong it is. Okay, p-value is what is the probability? Probability you can get more rare cases than your current x bar. So when we talk about the mean, sample mean, you got some sample means, right? So what is the probability you can get a rare, more extreme case than this number? What is the probability? So its greatest case is this is my x bar or the z value. What is the probability you can get a greater than my x bar, or this case is smaller than the x bar? And then if that probability is less than 10% or less than 5% or less than 1%, you're gonna reject the null hypothesis. So more rare case, you're gonna reject. Now we will take a look the same thing, but now we will decide to use a two-tail test. It can be smaller or it can be greater, but whenever it's changed, we're gonna fix our machine. So null hypothesis test, null hypothesis will be the mu is the same as 216, but alternative hypothesis is not 216, something changed. We have to adjust our machine. In this case, we have to, if it's a smaller or bigger, both sides we have to reject. So our alpha, so if you use the same alpha 0.5, this will be divided into the 2.5% here, 2.5% here. So that's why it becomes a 2.5 and 2.5. Okay, so if you use a critical value, you can find out this is the critical value method, and you can, if you compare you can calculate the z value and then compare to the 1.96. Why this number changed? It was previously it was a 1.645 because this is the one tail. Previously we used a one tail test, but now this is a two tail. That's why it becomes the z value is getting greater. Now you can calculate the z value of the 216.007. Yeah, we already know the number, but this number is still greater than this. What was the... So still you can reject null hypothesis. P-value method, we will find out the probability that our z is here, but we will calculate the probability, then we can get a greater than 16.007. What is the probability your x bar will be greater than this one? So we will find out that the probability of z will be greater than 2.152. This is our z value, right? So if you calculate it, then the area will be 0.0157. So how can I find out? It's a z value is 2.15. Z value is 2.15, right? So probability is 0.9842. So probability is the 0.9842, which means this probability will be 0.018. 0.0158, 0.0157. Yeah, because we have a slightly different, this is slightly different. Now, what is the probability you can have a more extreme cases than your case? This is your case. X bar is to 16.007. What is the probability you can have a more extreme cases than your cases? Is here, or you can have a, if you got a smaller than minus 2.152, it will be symmetric, right? So it will be same. So times 2 will be the probability that you will get a more rare cases than yours. The summation will be still about 3%, right? Which means what is the probability that more rare cases than your case is 3%. So since we are using 5% confidence level, so our 216.007 is really still the rare case. Rare enough because our cut line is 5%, but what is the probability that I can get a more rare case than my case is just 3.14%. So which is small enough because our cut line is 5%. So this is still the rare case. So my assumption of my mu is 216 is not true. Because if it's true, getting this is really rare. So which means it's probably this is not true. So we reject null hypothesis. So we can conclude by 5% confidence level, 5% level, we think our mean is not 216. So which means we have to adjust the machine. If you consider the analogy to the confidence interval is the two-tail hypothesis testing. So this is the when only the two-tail cases. If you calculate the confidence interval first using the X bar, right? And if the 216 is not fall in between here, then we can reject. Actually, if you calculate it, the range will be 216.001 to 216.013. So 216.000 is not fall in between here, it's outside, which means probably your mean is not 216, so we reject. So again, this is another way to use a confidence interval. Maybe you can consider this is third method, but the conclusion will be always the same. Using confidence interval or using p-value or using the critical value, conclusion is always the same. This is only which level, which number we will use to make a conclusion.